So hello everyone, my name is Swapnil Puri, and today I'll be presenting my project on exploring vibration-simulated Braille for accessible mobile messaging. And to start, I thought it would be important to give a little context as to what Braille is and its importance. So Braille is a tactile literary system that allows individuals to read through touch as opposed to through sight. And it uses a combination of 6 dots, raised or flat, and inside a 3x2 grid or cell to represent different characters, symbols, numbers, etc. And this is primarily employed by individuals with visual impairments as a way of independently accessing written text, much like how printed text allows us, sighted users, to access information. And even beyond information access, Braille has been linked to self-esteem and overall well-being, showing that in many cases, Braille is much more than just a tactile literary system, but for many users. With this in mind, what is the primary issue today? Well, information has become increasingly digitalized, with many forms of content being almost exclusively available online and only accessible through electronic devices such as computers, smartphones, and laptops. And this presents a problem when we realize many of these devices, these conventional and modern devices, lack the integrated and native Braille support needed to actually feel whatever content an individual sees on a screen. And so for visually impaired users who are comfortable using Braille, now this presents a problem. And now to access content online, they're forced to use workarounds. And so what are these workarounds? Well, one of the main workarounds are refreshable Braille displays. Now, this is an external piece of hardware that extends a computer or a device to allow users to tactically feel whatever content they encounter on their screen. There's a variety of different prongs that raise and lower to create Braille cells that a user can feel. And now, while this can work, it is often inaccessible due to its immense cost and for other disadvantages associated with it, including excessive sound as well as portability issues. And so what is another popular workaround that visually impaired users employ? Well, there are audio-based technologies such as text-to-speech or screen readers that convert what is once visual or visual text into something that is now perceivable audibly. And this also is employed and can be effective to many. However, it is not accessible in instances where an individual is visually impaired and does not have hearing, and in other circumstances, social circumstances, where quiet is necessary, it can be inappropriate to use these technologies. And lastly, again, it ignores the tactile and physical benefits associated with Braille that I mentioned briefly earlier. Luckily, researchers have begun experimenting with the one physical sensation that many smartphones do possess: vibrations. And so researchers have first come up with vBraille, which is a smartphone application which segments a phone screen into 6 different regions to correspond to the different dots within a standard Braille cell. And the whole premise of the app is that an individual would press each section of the application and either feel a vibration or feel nothing. The vibration would indicate that that cell is supposed to be a raised dot, and no vibration indicates that that cell is a flat dot. And after pressing every single section, a user is expected to be able to construct that Braille in their mind and identify what character it corresponds to. And researchers have found that this is fairly well-performing, and as users were able to accurately identify the correct character around 90% of the time. And so another form of vibration-simulated Braille that researchers have employed includes Braille rhythm. And now this, unlike vBraille, is not positionally dependent. You don't need to press different areas of the screen, which could have some problems. Maybe you accidentally tap on the side or some other issues arise. Instead, vBraille had a user place a stylus in one section of the screen and feel a sequence of 6 vibrations. Those vibrations could either be strong or weak to represent a raised dot or a flat dot. And a user was supposed to take in those 6 vibrations, construct a Braille cell visually, or in their mind, going from the top left all the way to the bottom right, and be able to identify what character that is. And through those studies, researchers have found that it was more accurate and often resulted in quicker judgments, as users did not have to travel across the screen to gather information. However, while these solutions do in fact work, they suffer a significant limitation. They were designed for primarily experimental evaluation. They conducted simple tests. The apps were entirely based on simple tests and simple tasks like single letter recognition, but in the real world, visually impaired users would want more than just to read single, isolated, and random letters. That is not useful at all to the target population. And so, ideally, an app, visually impaired users would ideally want an app that is fully comprehensive and functional to allow these users to glean whatever information is necessary and that they can rely on consistently on a day-to-day basis. And so that is the primary research gap that I've identified, is that there's no comprehensive mobile application that employs vibration-simulated Braille in a way that effectively conveys meaningful information, not just single letters, to visually impaired individuals that they could genuinely use on a day-to-day basis. And so I sought to fill in this gap. And naturally, I thought about what application would best benefit from this. And I thought, where would there be constant inflow and exchange of information that a user would want to read? And so I thought about a mobile messaging application and later derived the question, how can vibration-simulated Braille be integrated into a mobile communication platform to enhance accessibility for these visually impaired users? And so now that's where we arrive at the solution that I have developed. VibeCom is a multimodal iOS application that is designed with accessibility at its core. It allows users to send and receive messages from their friends, and to send messages, there's 3 main modes. There is a gesture-based Braille input, where a user would swipe right or left, right being a raised dot or left being a flat dot, to construct a Braille cell a dot at a time and send that to their companion. There's also a drawing pad in the event that an individual is developed visual impairments later in life and they were comfortable with drawing letters. They can use that to draw simple letters like A, B, C. And lastly, there is a regular traditional keyboard for the sighted users. And for output methods, there are 3 output methods as well. There is a vibration-simulated Braille, which in this system works a lot like the Braille rhythm, in that a user receives 6 different vibrations for each letter that's in the message that they receive. There's also, they can also hear the messages audibly through a voice synthesizer, and there's a visual interface, again, more geared towards sighted users. And on the more technical side, this application was developed using Apple's Swift UI, and back-end services were handled using Google's Firebase. And to pair with this app, I also created a secondary app that was supposed to be used in tandem with VibeCom, and is essentially an accessible way to add friends based on those who are nearby, and to chat with them in VibeCom. And now this uses similar accessibility principles as VibeCom, as well as has a similar technical makeup to it. And so now to better demonstrate the system, I will play a short demonstration.
Today I'll be demonstrating VibeCom and VibeConnect. I'll start with VibeCom, which is the core messaging app, and then show how VibeConnect integrates with it. When you first open VibeCom, one of the key features is the Braille mode toggle. This switches between standard mode and Braille mode. Standard mode works like a typical messaging app for sighted users, Braille mode, on the other hand, introduces gesture-based interactions and additional feedback designed for visually impaired users. You'll notice that the toggle requires a long drag. This is intentional, to prevent accidental switching. Braille mode is on by default, making it easier for visually impaired users to stay in their preferred mode. I'll start in standard mode. Here, navigation is familiar. I can tap into a chat and go back using the top left button. Inside a chat, I can type and send messages just like any conventional messaging app. Back on the home screen, I can search for specific contacts using the search bar. Now I'll switch to Braille mode. In this mode, the app becomes gesture-driven rather than visually driven, with multimodal feedback replacing reliance on the screen. There are a few core gestures. 2-finger swipe left to enter a chat, 2-finger swipe right to go back, swipe up or down to move through chats or messages, and a 3-finger tap to switch feedback modes. There are 3 non-visual feedback modes: speech, vibration, and combined. Speech mode reads content aloud.
Friend said nothing much. You said cool.
Vibration mode simulates Braille by using patterns of soft and strong vibrations to represent the 6 dots in a Braille cell, with each sequence forming a character. Combined mode uses both. Since vibrations are hard to demonstrate here, I'll simulate them with high and low-pitched beeps. In a real setting, this would be tactile. Inside a chat, you'll see the Braille pad. Users can swipe left or right to build Braille characters, left for a flat dot, right for a raised dot. For example, I'll create the letter O. Other gestures include single tap for a space, shake to delete, double tap to send. This allows users to type entirely through gestures and feedback. There's also a drawing pad activated by holding down the Braille pad. This is helpful for users who learn to write visually and may prefer drawing letters. I'll write a quick word to demonstrate. Chats are automatically linked to your contacts. If someone in your contacts uses the app, they appear as an available chat. No need for friend requests or manual searching. While VibeCom focuses on messaging, VibeConnect handles friend discovery. It's a separate app to keep VibeCom simple and focused. And in VibeConnect, I can discover nearby users using location. Here, I'll demonstrate how the app works across 2 devices. This app allows users to swipe right to add someone to their contacts, swipe left to skip, 2-finger swipe down to find users on the same network, 2-finger swipe up to view added contacts. Once added, these contacts automatically appear in VibeCom. Now I'll return to VibeCom and demonstrate a fully non-visual interaction. I'll turn on stealth mode, which removes visual dependence.
Stealth mode enabled.
While in stealth mode, another user will send me a message saying, "Hey." Using only feedback and gestures, I can read and respond.
Chat with 222 222 2222. Friend said hey. Age. I. You said hi.
Now I'll turn stealth mode off,
Stealth mode disabled.
and you can see the conversation. The key takeaway is that this interaction can happen without relying on sight at all.
And so now discussing the future work and the potential of this application if development were to continue, there are a few ways that this system could benefit from usability studies with visually impaired users to see how the application could be refined and changed to their preferences as they are the target audience. There are also other additions that could be made in terms of making more customizable accessibility options, such as adjusting the speech speed or the intensity of the vibrations so that these can be tailored to each specific user's needs. And lastly, there are some more general and conventional and convenient features that could be added, like a group messaging system, so that not all messages are just one-to-one. And finally, in conclusion, VibeCom and VibeConnect represents an accessible and more comprehensive approach towards mobile messaging through the use of multimodal feedback with a pronounced emphasis on vibration-simulated Braille. which represents a way through smartphones to convey information without relying on sight or on audio. And so the purpose of this system is not to replace the current existing mobile messaging giants, but to rather demonstrate how it can be possible to introduce and adopt these alternative input and output methods to tailor to another and a large population of users and expand accessibility of not only the app, but in information in general to more users. Thank you all for attending, and I'll be happy to answer any of your questions.
Swapnil, I would love to know how you came to be interested in Braille or in digital representations of Braille.
Yes. So I've always been interested in the accessibility side of things. When I would work with websites, I would always be interested in how you could make websites more accessible by adding in alt text so that users who are using screen readers could know what they're witnessing without having to actually see things. And so I've always been concerned about how we can make different applications more accessible. And I initially thought about Braille and how it's only really been applicable in a physical sense and really hasn't been applied in the digital realm. And I wondered, is there any way to actually relay that information, that physical information through these devices? Initially, I was thinking about it why isn't there any way to just feel out Braille itself? Maybe just have different sections that when you press a section, it would vibrate in that area, right? But then there's hardware constraints associated with that. You can't pinpoint a vibration to a specific location, right? If you want a vibration, it's going to vibrate the entirety of the phone. And so I had to kind of segue into thinking about a new way to represent vibration. And that's where I came up with, or I found the research associated with the ways that people have already used vibrations to convey information. And I was really inspired by particularly the Rhythm Braille one as a way to convey information. And I wanted to put that into a full-scale application.
That was incredibly cool. Yeah, I'm sure there are a lot of questions.
Okay, so I'm interested. I know after COVID and over time, I think people are maybe reading novels less, and the long way, and more people are doing audiobooks. I wondered if the same has happened with Braille. If people are using Braille less and doing audio more, assuming that they have hearing, or whether Braille is just as popular as it's always been.
Yeah, so audiobooks have definitely impacted Braille literacy to a decent extent, but Braille is still used, and it's still the widely accepted form of relaying information to visually impaired individuals. And although, yes, COVID certainly and the audiobooks have affected that, I don't think that Braille will ever probably dissolve from being the go-to standard way of communicating. And so I think it's still important to make applications that still utilize Braille in a certain capacity to ensure that we tailor these applications to anybody and anyone. Even if it's not popular anymore, just making applications that can tailor to anyone is important.
I was wondering, a lot of people do talk to text. Is there a way to talk to vibration? Can you think about a way to incorporate that into your say a message, and then that gets the output to the person who
The output is,
Yeah.
the output is still what the vibration.
Yeah, so that is one input method that could be implemented. I did not end up implementing one where it uses audio as opposed to the other ones. And that's more so because my primary focus was on the vibration-based Braille, but it certainly is an area for future work and improvement of the application itself.
I'm going to invite your advice. That was so cool. Very impressive. I'm going to invite your advisor, Dr. Shavaro, up to say whatever he would like about getting to work with Swapnil, and also be presenting the cord and stole that he'll wear at graduation just like Mary, this represents not only this really impressive work, but 4 years of really impressive contribution to the honors program. So congratulations and thank you. I'll turn things over to Dr. Shaparo.
Yeah, I had a real pleasure working with Swapnil on this project. Believe it or not, a lot of software engineers forget adding accessibility options to their software and products. So I was so excited when he came up with the idea. We both didn't know much about it, but we were all for it, and we were like, whatever it is, we're gonna keep going and trying to figure things out. So this is one of the research projects that we really enjoyed together and learned together about it. And I appreciate you being also patient with my picky. And we were like you saw this little slider that is switched from Braille to no Braille mode. It was much shorter, and it was like, make it bigger, and then next meeting, make it bigger, so that we avoid having that accidentally clicked. And we visited all kind of input and output methods for texting, and we were looking at privacy as well. You saw like we were focusing more on the blind or the visually impaired people, but also we were thinking, what if this visually impaired person is also deaf and can't hear? And then also we looked at the stealth mode. You saw that we looked at if you're blind and you're texting, the person next to you, we don't want them to see what you're texting, right? So if they cannot see it, the person next to you shouldn't also invade your privacy by seeing the text. So there was a lot of details we looked at. The funny part, I would say, is we stared at the wall in my office a lot more than the app, because we were pretending, we should be able to work with this app without looking at the app. So that was very interesting. So congratulations on great work on this project and all your 4 years.